Did y'all bring Smith charts with you? And straight edge. Yeah. All right. I prefer we do one of each. One inside the R=1 circle, one inside the rotated circle, and then one outside both. And I'll talk my way through how you go about the matching. All right. So I'm going to just put up a generic Smith chart as best I can. Here, you have Smith charts, and I sent everybody the best one I knew of in terms of the amount of resolution size of it that has a rotated circle as well. So that's the R=1 circle, and here's the rotated circle, my version. All right, now, last time we did one where we had something inside the rotated circle. I'd like to go through that kind of quickly if you'd help me. If you've got a problem you want me to do that has a load impedance that is greater than in magnitude Z0, in other words, we're going to do case 1 here, and this is where you're inside the R=1 circle. So case 1 would be magnitude of ZL over Z0 here is going to be less than 1. So that means that ZL, the normalized ZL, will be inside the rotated circle. And this, of course, will be ZL over Z0. So do you have one in mind, or you want me how many did the problems? Is it the second one I assigned not, I'm trying to think of the number on it. It's not 31, but is it 33? What was the problems assigned, the numbers on them?
It was 10, 13, 14, 15, 16.
14, give me 14, please. We'll do that.
Match network, blah, 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 and 80 minus J 50 ohm load to a 50 ohm line.
Okay, so we have ZL is equal to 80 minus J50. What's Z now? 50?
Yes.
All right. So this is classic. All right. Here, obviously, the magnitude of the load impedance is greater than 50 ohms. You all agree with that? We know when we normalize, we're going to be inside the rotated circle. Let's do it. So that means we have 80 minus J50 over 50, right? And that's going to be, what is that, 1.6, right? You all agree with that? That's normalized, 1.6 minus J1, right? Now, let's locate that. Well, first, I know that this is J1 here, and this is the south pole is minus J1, and this will be the corner of a circle, or the center of it's there, and this is the minus J1. So if we look at 1.6 minus J1, the 1.6 circle would be about here. You're going to have to estimate that. And this should be normalized ZL. Do you all find that, class? Take a look on your Smith charts. Now remember, this is like going to be 1 right at the center. Then the next one may be 2. It's logarithmic, or not logarithmic, but it's not a linear scale here. So there's like 2, and you got to estimate where 1.6 is. Is it 2 the next part, or is it?
No, it has 1.6.
Yeah, I was going to say it's on it.
It's on there, good. So anyway, you can locate that point, right?
Yes.
Normally, I recommend you put a number there, 1. That's your first point. It's called the entry point. Y'all see that? It's inside the 1 circle. No matter what we add to that, we can only move on this trajectory right here. Y'all with me? No matter what reactive component. We can add to or remove the reactive component, but we can never get outside that 1 circle, and our whole goal is to get right to the center here. That's the goal of this whole exercise. So we go to the actual admittance domain. This is impedance. We go right through here, and this is point 2. And this would be Y load, or 1 over Z load. Can you just give that to me? Take 1 over that, and we got it. It's going to be, I don't know actually, 0.25. plus J, oh boy, I can't do that.
It's 0.45 plus J 0.28.
4, 5 plus J what?
0.28.
Okay, can you all see that? Yeah,
So how do you get the YL again?
it's 1 over ZL. ZL is the normalized load impedance. And ZL you get by taking the load impedance dividing by Z naught. The whole idea is this. We have a load impedance, ZL. And then we have Z naught as the characteristic impedance of the transmission line. It might be a strip line, it might be coax, we don't care, but mostly it's strip line, all right? And then what we're gonna do is find things, small elements to put in this circuit that won't cause a lot of real estate to be used, like stub tuning would. In other words, not a lot of the actual surface area that shift. So what we're gonna do, when we're in the Y domain, we're about to find out the value of Y we put in here, right? And y'all see where this is right here? Can y'all look at that? Yeah.
So how do we know where to draw that line to?
If you really wanna know the truth, you go right through the center of the circle, take your compass and just, you could arc, put a circle there, and then take a straight edge, go right through. But this length is the same as that length, and it's right, it goes right through the center.
But does it stop on the circle on the left side, or does it?
You see this point ZL, you know how to find that? All right, the only thing you do is go from this point, dead center, this is the reflection coefficient equal 1, it's the center of the circle, move to there. This length will be this length, and it's a straight line.
So
if you
calculate YL first, and then draw it to YL.
Yeah, but the normal procedure, I'm just trying to get you to do this in a way, initially, you don't know where it's gonna land.
Okay.
Technically speaking, you don't know it's inside. You do and you don't, right? So it's always smart to start there with ZL. And the first thing you can see is no matter what I do to that in terms of a series impedance, I can't get it's not gonna have a real value of 1. So that means I go to the admittance domain. Now, I'm on a circle that has, the real part here is 0.45, right? The real part of this is 0.45. So there's this circle that's gonna have that's gonna be the 0.5 real trajectory. Do y'all see that? Do you see what I'm saying? Guys, can you see it in the back? All right. Now that trajectory is where you're on now if you're the admittance domain. We can add admittance reactions, but either plus or minus J here, it'd be in parallel, and we can move along this line, and that's ideal, because we're gonna move from here right to this point where we're on this rotated circle. That's our goal. With me? Now, I don't know how far that is. Can you go ahead and tell me on this rotated circle where the 0.5 trajectory crosses? Can you tell me that, Bethany?
So we draw the line from YL to the circle?
Well, what I want you to do is note this. See this real component?
Yes, sir.
All right, you see where that line is approximately? Just look, it's a trajectory. Forget about the imaginary, it's just a real value of 0.45. Do you see that?
Yeah.
All right, if you move on that trajectory, it will intersect with the one circle.
Okay.
Do you see that?
Yes.
Do you see it in the back?
How long is it?
So you're saying like you go from YL and you go this way? And you hit
Well,
that
you know
circle?
when I say the 0.45, do you know what I'm talking about when I say the trajectory? There's a circle that has a radius of, do you see it?
Yeah.
Like, go from.
Show him, would you?
Yeah.
Yes.
Do you all see it? Does anybody not see it? Because I want to make it, when I'm talking, if you don't understand what I'm talking about, let me know, and I'll try to make it clear to you. It's real important you understand what this means and don't have any gaps here, because it's essential you see this.
I know what circle the 0.45 circle is, but what are you saying we're doing with it?
We're going to add, see, this has a real and imaginary part, right? What we're going to do is find out the difference in the imaginary part here and here, and we're going to add that much imaginary so we get on the one circle, or the rotated circle.
Okay.
All right, that's the goal.
So you want the length and wavelengths?
What?
From the
reasonable question.
YL to the circle, you asked for the length of it. Would I give that like in wavelengths?
No, in the difference in the J values.
Oh.
See,
Sorry.
I'm trying to make sure that we understand that what we're going to be doing is adding an admittance. An admittance has a J something, in this case a positive J something. Y'all follow me? All right, look up here for a second. This is drawn it's drawn kind of crunched down, but if you move from this point on the 0.45 trajectory, I'm at 0.45 plus J.28, right? Suppose I add J.2 to it. That would give me a value of J.48, right? That's not where you want to go. You want to go right to this point where it's rotated, right where the 0.45 intersects this rotated circle. Can you give me that value?
It's 0.5
0.5?
for the J. Yeah.
All right, so this point where it intersects would be 0.45 plus J 0.5. Do you all agree with that? Now, this should be obvious. We're adding admittance, right? So, I started at J.28. Y'all with me? How much do I have to add to get to J.5? Well, it'll be 0.5 more minus 0.28, right? And that's 0.12?
0.22.
Or 22, I mean, 0.22. So here, what we're gonna say, I'll move this out. This is gonna be J 0.22. That's an admittance. It's normalized, right, class? Y'all with me? Okay, that's how far we have to go. That's how much we have to add. So this would be my third point right here that I'm at, right? After I add this is all normalized. Maybe I should say, yeah, no, I'll leave this as ZL here. It's still Z now as a characteristic. Now, I'm at this point. It's an admittance, right? Now I go to the impedance domain. So I whip back over here, and I'll come and I'll intersect this point. This will be 0.4. Y'all follow me on this? Now remember, the only thing I'm doing is viewing this as either an admittance or an impedance, simply because I'll be adding elements in one of the two domains. I'm going to add something, and my whole goal is to get rid of the reactive part and have a real part that's normalized right at the center. That's the goal of this exercise. Y'all follow me? All right, now, I'm here. So take this, that's at the rotated point, right? And take 1 over that and give me the normalized impedance associated with that, which would be 0.4. And better have a real value of 1 or you did something wrong. Close to it. It won't be exact. It'll be 0.99 something.
1 minus J 1.1.
All right, 1 minus J 1.1. Do you all get that, class? All right, that's 0.4. Agreed?
What did we type in to get 1 minus J 1.1?
You see this value here? That's on the rotated circle. That's an admittance, right?
Okay, and that value,
Now,
that value is the 0.5 plus J 0.5? Or
it's
0.45?
0.45 plus J.5.
Okay.
If you take 1 over that, you're gonna, see, the whole idea is when you're on this rotated circle in the admittance domain, the minute you go to the impedance domain, you're still on the 1 circle. You're on the other rotated rim, you might say, the 1 circle. And that's where you wanna be. Got me on this, guys? So we're here, and we're at 0.4, we're right here. Now, hear me. Remember, this is going to be an impedance. We add an admittance, now we're going to add an impedance, right? How much are we going to add? Well, we want to add something to get rid of that J minus J 1.1. We add a plus J 1.1. Y'all follow me on that? You with me, Carly? Or can you see this right here?
I see it. I'm not getting the same thing, but I think it's okay.
Take
I'll figure
this
it
and
out.
take 1 over that.
Okay, I need to do that. I didn't do that.
Just show it. You're right there. Normally, you should just be able to take 1 over. Do you have a 1 over function on your calculator? I don't know how they are anymore. My calculator used to have ln on it. I don't know if they still do or if it's all log base 10, and you have to have a function key to get a natural log. So there's a lot of weird things that have happened in calculators.
We can do both of them.
Okay, well, it's an advanced version. Anyway, now y'all see how to get this, Carly?
Yes.
All right,
I got
and
it.
all you guys, Clay? All right, now, listen, this is, at this point, it's pretty obvious. The only thing I wanna do is add something to get rid of that minus J 1.1. Well, that's a plus J 1.1. Y'all follow me? It would be in series. It would be an impedance. So this is gonna be J 1.1. And that's what the circuit looks like in terms of the normalized quantities that we've added. Are you with me on this? Now, we're gonna go find the values of the elements, the actual elements, the capacitors and inductors, all right? So, the first one I'm gonna do is the inductor here. All right, a plus J impedance is always associated with an inductor. Y'all with me? The normal impedance of an inductor is J omega L, right? If you normalize it, it's just J omega L over Z naught. It's still positive. That's the idea. This is a positive J, it's an inductor. So now we find the value of that. I know that for an inductor, the impedance of an inductor is J omega L, where omega is 2 pi F, right? That's just the normal the unnormalized impedance. It's the measurable impedance. Now I normalize it, I divide by Z naught. So when I divide this by Z naught, now I can go ahead and simply equate that to J 1.1. You follow the reasoning on this, everyone? You guys back there got it? All right. So that means this is equal to J 1.1. I can remove the J, obviously. And now I'm looking for the elemental value L, right? Class? I know this becomes kind of obvious at a point, but just work through the whole thing with me. There are some subtle mistakes people make. Most of the time, it's over here. So that means L itself would be 1.1 in this case, right? Times Z naught over omega, or over 2 pi. What's the operational frequency on this one?
1 gigahertz.
All right, so it's times 10 to the 6th, or 10 to the 9th, pardon me, 10 to the 9th. And Z naught is 50, right? So can you tell me the value of L for that? You won't get exactly the right answer, but you'll get close enough for all intent purposes.
8.75 times 10 to the negative 9.
All right, that's nanohenries, right? 8.71.
75.
That's small, by the way. I'm just going to say this: when you're buying components, you kind of have something in your back of your mind. If you get a capacitor of 1 femtofarad, 1 times 10 to the minus 15 farad, that's not something you buy. That's so small, practically speaking, any length of wire bent on itself will probably have at least that much capacitance. I'm just going to tell you it's an unreasonable amount to use any kind of engineering with. An inductor getting down to picohenries is also outside the realm of what you can engineer with effectively. It's just too small. It's like a resistance of like 10 to the minus 6 ohms. Now you're talking about a half a degree of temperature on whatever's near it will change the resistance at least that much. All right, got the value of the inductance. Next is this, is the capacitance, right? You all agree that now I'm going to do this the way I prefer to do it. I like to work with impedances and then get admittances, and here's why. Most